Okay, thank you, Abhishek. So I first like to thank Abhishek for organizing this series of summer schools. They have, Abhishek and Sanjib have been doing it for a very long time. It's a lot of work, but it is very, very useful. And then, of course, for asking me to talk here now. So I thought I will discuss some models of hardcore particles with hardcore interactions. And we have been working on different aspects of this problem for a fairly long time. And at least I find them quite fascinating. And what I would like to try to do is to convince you that this is actually an interesting problem to study. And there are a lot of open-ended stuff which you can try to work on later if you feel like. Okay, so let us just start. Okay, so this was an outline, and see, when I said initially given the title, I had said hard rods, but it has been changed into hard particles, which are not necessarily rod-like. And even this outline was given some time ago, and it will not be strictly followed. So let us see how it works. Okay, so of course, the problem of phase transitions has been sort of an important problem or the key problem people have been worried about for over 50 years. So why is the problem of phase transitions the central problem, or has been a very, I don't know if it's the central problem, but very important problem in statistical physics? So there is this general formalism of equilibrium statistical mechanics where there is a partition function and all the properties of the system follow from the partition function. And then in the partition function, things like the various parameters like the temperature appear as a simple parameter. Partition function is a nice sum of exponentials of exponential minus beta e. And it is hard to see how some singularity can develop as a function of beta in the partition function. So in the beginning, people were not sure. In beginning means around 1900. People were not sure that the formalism of statistical mechanics could describe both the phases at the same time. So they said there could be a theory of liquids and there could be a theory of solids. And you know, whenever the free energy is less, you go to the theory of liquids, otherwise you go to the theory of solids. But it was realized around 1930 or so that actually you can take the same model and the thermodynamic limit makes the phase transition possible. And so that is the mechanism of phase transitions. And then, you know, then people tried to find models where you could solve them exactly. And I guess there is no hope of being able to solve for the exact equation of state for most known materials. Okay, so instead you try to find some prototypical simple models where qualitative behavior is somewhat similar, but maybe it doesn't give you the exact equation of state of water. And so, you know, that's the question. Can we find some systems where one can actually study these phase transitions very well, starting with this model, starting with the theory of equilibrium, stat-mech theory of, you know, partition functions and things like that. And so I start with this simple picture of the phase diagram of water. So the axes are pressure and temperature. And one usually says that, you know, there is a solid phase, then a liquid phase, then a gas phase. So if you keep the pressure constant and increase the temperature, you go from solid phase to liquid phase to gas phase. And if you change the pressure, the melting point and the boiling point can change. And so this line gives you the temperature dependence of the melting point with pressure, and this line gives you the temperature dependence of the boiling point with pressure. And this line here, when you heat, the solid directly goes into gas. That is called sublimation. Okay. So this diagram is well known and well studied, well known at lower classes. So, but let me just say this. So the first question which comes into mind is that we are discussing phase transitions. So what is a phase? So, well, I guess you take something like solid phase, which in this case is ice, and you change the temperature and pressure a little bit. Then the properties of ice, like the density, will change a little bit. But we say it is still a solid. But when you go here and change the temperature a little bit, then we say it is a liquid. And so what defines a solid or a liquid? And the answer is that you have to find a question which is, in the end, it is something, is this a solid? We will qualify this, what does it mean? But the answer here, you change pressure and temperature, but it says yes, 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 and here it says no. So there is a transition from a phase which is a solid to a phase which is not a solid. So it's a phase transition. Okay? Now, what is the question which distinguishes a solid and a liquid? That one, you know, people have given all kinds of different definitions, but for the moment we will say that, okay, if you take X-ray pattern of the X-ray diffraction picture of the material, if it gives black peaks, then it's a crystalline solid. If it doesn't give black peaks, it is not a solid. So this transition is easy to understand. This transition, liquid-gas transition, is a little bit more problematic. So what is the yes-no question you can ask to distinguish between liquid and gas? And so it is known that there is a critical point beyond which the distinction between liquid and gas is not there. And so if you change from here and change continuously, you can go here. So it's not possible to form a yes-no question which will give you the distinction between liquid and gas, except an arbitrary definition. You can always say that if the density is more than some number, then it is, you know, draw a vertical line here, that anything on the left of the vertical line is a liquid, on the right it's a gas. But such a definition is very arbitrary. Okay? And we try to avoid artificial definitions. So in practice, the liquid and gas phases are the same phase. They are called fluid phase. These are the phases which flow. And so when I go from liquid to gas here, I go from the same phase to the same phase. So how is that a phase transition? This is sort of a very simple question, but it seems to be confusing to the students often. So I guess what happens is that here the density is high, and all of a sudden there is a jump in density. Past the boiling point, the density is very low. And so there is a discontinuous change in density, in which case there is a qualitative question. You can say, are you in the high density phase or are you in the low density phase? And that is sort of the way to mark out this line. This is the line where the density discontinuity occurs, but there is no, the phases on the two sides are the same. Okay, so sometimes one gives this definition of phase transition. A non-analytic response to a small perturbation is signal of a phase transition. So here, there is no yes-no question you can make to go from liquid to gas. But you can see I changed the temperature only by microkelvin, but the density has changed by a huge amount, and so there is a phase transition from the same phase to the same phase. From the fluid phase to fluid phase, there is a phase transition. Okay? Okay. So general theory of phase transitions. I thought it would be useful for the students to have some background because, sometimes these questions are not adequately addressed because they go very quickly into technical calculation of critical exponents. Okay, so general theory of phase transitions. To a very good approximation, molecules interact by pairwise additive Lennard-Jones type interaction. So we are starting with real materials like whatever matter you have, water or alcohol or copper. And so I want to model this. So how can I try to understand this theory of phase transition of copper in a sensible way? So copper is a little bit complicated. It has all these metallic particles, and in the solid phase there are electrons, and they kind of roam around freely. So let us take some simpler system like argon. Argon is an atomic material. Molecules are the same as atoms, and atoms are sort of like hard spheres, and so that is a simpler solid to consider. You can consider more complicated ones, but let's work with sort of simplest ones. So the interaction between argon atoms can be approximated by just a pairwise potential, which is a function of the distance between the nuclei. So that is the V of R. It is repulsive at short distances and attractive at large distances. Okay, so it has the general shape. We will not be really bothered about the exact functional form of V of R. It is sometimes written as 1 upon r to the power 12 minus 1 upon r to the power 6. That particular detail is not very important. You can take more general forms and it behaves roughly the same way. So long as the potential has this rough shape, most of the properties seem to be somewhat similar. Okay? So that is what is meant by Lennard-Jones type, and this word is additive here. Additive says that if you take 3 atoms and calculate the energy of this assembly of 3 atoms, that will be more or less equal to the energy of taken 2 at a time. V total is equal to V1, 2. Let's write it. Plus so what is this E? This is the energy of the 3-particle system at when I freeze the nuclei at R1, R2, R3. So what do the electrons do? They satisfy the Schrodinger equation. You go to the ground state of the system. There is a ground state energy corresponding to 3 nuclei fixed and electrons in the ground state. So that is the energy eigenvalue is E1 to 3. That is the definition, because the system could be in some excited state, but we are looking at the ground state. And so this energy, if all the particles are very far from each other, will be just the sum of 3 energies of 3 atoms. That is the constant. And then the correction to this energy, because the atoms are nearby, is called this potential energy. and V12, okay, so above this. So it is very clear that in principle I can calculate this energy V12 by quantum mechanical, first principles quantum mechanical calculation. I just have to solve the Schrodinger equation and that gives me the energy. And then I can calculate E123 by the same method. And I will ask, is this equation, V12 is now known. So is the second equation true or not true? And the answer is it is not exactly true. It is only true a very good approximation. And so there are three body forces or potentials which are there in real atoms, but their effect is not very important. And in theoretical discussion, we will say that, okay, the model in which you don't worry about three body forces is adequate, okay? But if you want to make a precise comparison with some experimental data for real liquids, then quite often it is necessary to add something like the three body terms in the interaction, otherwise it's very hard to get the data to fit. Now this is a complicated inverse problem. You have to, V12 is usually not calculated theoretically, even though I said it could have been. It's used as a fitting parameter. You write some function and see if it fits data. If you see Kittel's book, then he will say, let us postulate some form like this. Let us postulate so the 6 comes from van der Waals theory, for which there is some theoretical justification. If you take particles at large distances, they go like 1 upon r to the power 6. The value of B will be considered as a parameter which we will use to fit the data. And X, so what is X? What is the power by which the molecules repel each other when they are very close? Can one say from first principles what that power should be? It should be greater than 6, otherwise this form will not work. Okay? Yeah, it is taken as 12, but I am saying that from first principles, I can say that let's write this E 1, 2, 3 goes as 1 upon R12 for R12 goes to 0. If you take two particles very close and the third one is far away, then the dominant energy, which is the Coulomb energy between the nuclei, which are right now taken as point particles. So the energy will go as 1 upon r to the power r12. So if I use the same argument as I used earlier for, large R, the behavior is 1 upon r to the power 6, I should put x equal to 1. And then this form will not work, because then it will actually go to minus infinity. This form, the potential I get will be perhaps, it will be minus r to the power 6, but I can say r1 to the power 6 does not hold, as r12 goes to 0, of course. So it's not a real problem. But one should just appreciate that we are not fitting using x from first principles, but we find that in practice x gives good fit. to data. By that is meant that the potential I use is something like this. This is very robust, there is no doubt about this one. But if I can adjust this, I can say this is some function, but here it should go like some power, and I want to write a simple form. Then if you see what's the value of B at large R and what is the equilibrium separation at the minimum energy and that kind of stuff, then x equal to 12 seems to give a good fit. X equal to 1 will fit the data here. But this is not where I want to fit my data. I want to fit it near equilibrium, and there x equal to 12 is a better answer than x equal to 1. Okay, so we will use x equal to 12, let us say. And then A and B depend on material, and you can adjust them to give the spacing right and the bottom of the energy right for different, yes sir.
What do you get 1 over R, because there's also the electron.
Very good. So suppose you have two particles, 1, 2, and this is 3, and I bring 1 and 2 and even collapse them together. Then what will happen? This will form an atom of twice the atomic number. So it has a finite binding energy. Okay? But in the calculation of this finite binding energy, I have to add the nuclear separation to get the full answer. So the dominant term in the full Hamiltonian will be the potential energy, electrostatic repulsive and potential energy between the nuclei.
You're saying finally it comes not just from the electronic but also the nuclear?
No, when we did the calculation of E1 to 3, it had this potential energy, kinetic energy of nuclei, nucleus 1. This is the electron-electron energy, electron-nuclear energy, nuclear-nuclear energy. So when I calculate the potential energy of the atom, I take care of these terms. I don't explicitly write down the V and N. So this energy will have the energy which is the ground state energy of the joined atom, which is twice the atomic number, which has a finite binding energy. And
sir, also I think considering that adiabatic.
Sorry?
Adiabatic.
Adiabatic limit, very good. So here we have held the nuclei fixed in this approximation, okay? And then we calculate the electronic energy, and of course if the nuclei can move, maybe that calculation is not right, and there is a coupling between the electronic motion and the nuclear motion, which is approximately described in this system. This is called the Born-Oppenheimer approximation. What one says is that first you hold the nuclei fixed, calculate this electronic energy, and use this electronic energy as an effective potential in which the nuclei move. Okay? You can check or you can see immediately that that is actually an approximation. Unfortunately, going beyond the idea of this kind of approximation is very hard for anything other than hydrogen molecule. For the hydrogen molecule, I can imagine trying to do the problem in which I keep the coupling between nuclei and electrons together and see what is the correction to the energy if I take, if I make the Born-Oppenheimer approximation or if I don't make the Born-Oppenheimer approximation. Okay? I'm sure it won't be right, But the usual arguments, which is that the mass of the electron is much less than the mass of the nucleus, suggest that it is good to 1 part in 10 to the power 3. That doesn't sound so great. Okay? But it will not be much better than that, actually. So we are making all these approximations, simplifications to the original problem. We are saying that, look, there is all these, there are 3 body forces, but let's not worry about them. So this equality is not really an equality, is only an approximate equality. But we will take particles interacting by pairwise potentials. Okay? And the potential will be like that. And this point is not fully true by first principles quantum mechanics calculation, but it is good enough for our purpose, and we will take this as a fact and go on. It's not a fact, it's an approximation. Okay? I'm only emphasizing this because this is usually just not even said in 1 line in most treatments of the subject. Okay? So that's our interaction. And so if you put a large number of molecules in a box at long times, there is a unique equilibrium state. Okay? And in the equilibrium state, the probability that potential, the coordinates are Ri and momenta are Pi is constant exponential minus beta h. That is the Boltzmann assumption of the equilibrium state mech. It is justified, of course, but under some situations, and once in a while these conditions don't work, and then you get into some mess, So if you have glasses or something, then these approximations are not working. But we still want to describe phase transitions in glasses. Okay? And so where do we, sometimes people take for granted these top 3 lines, and then they keep on worrying that why is it that I'm not getting a nice potential which satisfies all the properties or something, or maybe the glasses don't satisfy the other approximations just as well. Anyway, so this prescription of equilibrium state mech is able to give you different phases and sharp phase transitions for the same H by varying temperature and pressure for large number of particles. You have to have the number of particles large, then one finds that if you plot average energy as a function of temperature for system of 10 to the power 3 particles, it has a smooth function, but if you take the number of particles bigger, it's still a smooth function, but may become sharper at around some point. And in the limit of large n, there is actually a non-elasticity which develops in the model. This is verified in simple models, in particular for the 2D Ising model, which was the first model where this could be shown explicitly. Okay, so this is the mechanism of phase transitions, and there is a theorem of Li and Yang where they showed how this singularity can develop as a function of n. I mention this because we will perhaps discuss this in some detail a bit later. Okay, so it comes in the basic okay, so now there is a, I have already kind of discussed this at some length, but there is a need for simple models, because even if you take this Lennard-Jones approximation, which is itself is a sequence of various approximations, it is very hard to study this model in great detail. So exact theoretical calculation using Lennard-Jones interaction has not been possible so far. I think one shouldn't say is not possible. Maybe tomorrow one of you will be able to solve that problem exactly. There is no proof it cannot be done. But it doesn't seem very likely that you can actually calculate the partition function of the Lennard-Jones solid or Lennard-Jones interacting system exactly. Okay? But one can do the following, one can check, take this interaction, put them on a computer and then see what is the equation of state. And then to good approximation, you find that with this model, you will get a solid phase and a liquid phase and a gas phase, which roughly nice, the volume will be correctly depending on temperature and so on. So there is no reason to doubt that these kind of models can describe the solid liquid gas transition, even though we have not been able to solve this problem exactly so far. Okay, so to understand better, we have to study even simpler models. We did this, but this is not good enough. So we simplify the model even further and see if we can solve the simpler problem. And so that is the need for simpler models. And then there is a hypothesis called the universality hypothesis, which says that different materials will of course have different equation of state, but at some level they look qualitatively similar. So if you take the equation of state of methyl alcohol versus ethyl alcohol or benzene, of course the melting points will be different, some behaviors will be different, but the fact that solid goes to liquid and it's a first order transition will perhaps be similar, and the second transition is also first order most of the time, and all these details will roughly be similar. Even near the critical point, the behavior will be similar. So that is the universality hypothesis. And so the universality hypothesis says that if you have critical phase transitions, then near the phase transition, the critical exponents will be the same. They will not change, they will be identical. Okay? But critically, so there has been a lot of work in the past dealing with critical exponents of all kinds of systems. And but critical exponents are not all there is to know. They are defined only very near some very special point. So I generally believe that the emphasis on determination of critical exponents is a cultivated myopia. Okay, so, people only look at that, they don't look at anything else, and this needn't be that way. So, but what one would like to do instead is to take detailed study of tractable representative of some phenomena under investigation. So our phenomena under investigation is a model which shows solid, liquid and gas phases. Can I construct a model which shows solid, liquid and gas phases? Okay, so one of the oldest models which is known is called the hard sphere model. And so one says, and I think even Dalton said something like this, that the molecules are roughly hard spheres. Okay, of course he didn't have, it was a guess. It's not true, these are not hard spheres, but they act like hard spheres, so they behave similarly as hard spheres. And so hard spheres of course don't have any attraction. So they have an attractive long distance coupling, and then at short distances, instead of having a potential like this, you can have a potential which is hard. Particles cannot get closer than some distance. Okay, that's a approximation. But the interesting point is that if you take the hard sphere model, just an assembly of hard spheres, put them in a box, and there is no interaction other than hard spheres, then, and all configurations which satisfy the hard sphere constraint are equally likely. This is a very simple statistical mechanical model. And so what can you say about this? So what happens, this is experimental fact based on Monte Carlo simulations, is that it shows a melting transition from a crystalline phase to a gas-like phase. At low densities, the spheres can be anywhere and it looks like a gas. Of course, there are some correlations between the spheres, but it looks like a gas. At high density, this system becomes crystalline. All the spheres arrange themselves into an hexagonal lattice. They jiggle around the mean position, but the fact that the lattice develops is true for densities beyond some density, and then so that is the so there is a transition from a solid-like phase in which there is a sharp X-ray peaks to a fluid phase in which there are no sharp X-ray peaks, and this transition is a purely geometric phase transition. The phase transition is described in this picture. There are hard spheres, and high density they look like this. A typical configuration looks like that. At low density, the typical configuration looks like that. Yes, sir. Wigner, I don't know about. Let's not. We can discuss it privately. Okay. So I'm discussing mostly classical statistical mechanics here. I mentioned the fact that quantum mechanics is needed to describe the basic interaction between atoms. But after that, we use classical stat mech with this pair potential and hope that that is a good representation of the system. Okay? Once in a while it is not. If you take liquid helium, then the fact that it's a quantum mechanical particle, there is some superfluidity, something, that is there. But we will not worry about it just now. When necessary, first we do the simplest things, and once they are done, then we can go to progress to more complicated stuff. So there is a saying of Chairman Mao. It says, first you should walk before you can run. I think it's very important. So maybe it's not all that you need to do, but you should learn to walk before you can run. So we will work with these simple models first. So I think that was the reason for putting up this stuff. Now it's very important to read. One of the objections to this kind of work, which is often made, is that, oh, this is so simplistic. And the fact that these models are simple models is taken to be a disadvantage, or I have to defend myself. Why are you studying such simple models? The real life is much more complicated than this. This is the standard argument which very wise colleagues, learned professors make. And I am giving a counter argument to that position. And it is quite possible that some of you will also say something like that with your friends later. But I'm giving my point of view, my justification that no, it is important to study simple things before you study complicated things. Okay, so this is a geometrical phase transition. The point about geometric is very important. What it says is that there is something like temperature which is important in stat mech and phase transition. And I don't need to invoke the word like temperature at all in the discussion of the geometric phase transitions. It's just a function of density of spheres, and there is no notion or no need to invoke temperature. So that is a simplification. I don't work with two variables. I have one independent variable, and I just study phase transition as a function of this variable. And okay. So as I said, that the transition between solid and fluids is not established analytically. It has not been proved that the hard spheres undergo solid to fluid transition, but there is Monte Carlo evidence, and I picked up this paper from this Journal of Chemical Physics paper. So here you start with some spheres at some density, and here they have started with some crystalline configuration on one side and sort of random configuration on the other side. And B and C are the final configurations. And one is at 11.70 and 11.45. So with a small change in pressure, the state is very different. This is the lattice formed by the system. This is a time evolved picture.
What are the white lines in the field?
So those are the lines which are the empty. The dark spots are the regions where the particles are seen. These are density maxima and white are density minima. It's a square lattice.
So you really have lines?
Precisely. So the size of this is not very big, so you can actually see the lines. It's a Monte Carlo. It shows a periodic crystalline solid in the second picture and absence of it in the third picture. P is the pressure. It's in some units which don't.
Is this 3 dimensions?
No, this is 2D. I think this is 2D. Because it will be very hard to do this simulation in 3D. I didn't check this very recently, but this is a Monte Carlo simulation and it shows you the crystalline phase, and if you change the density a little bit, the crystal disappears. So there are boundary conditions here which stabilize the crystalline phase, solid phase, the square lattice here. Okay. One can do other simulations. So, I'm only conveying the basic point that with a small change in pressure, you can see this actual change in a Monte Carlo simulation. And the details of the simulation, etc., I will not be able to defend personally in great detail. Okay, so with hard spheres there is also a complication. One usually says you get a periodic crystalline solid, but you can always take a layer and slide it against another layer. So HCP is a possible phase, but you can have a disordered set of layers. So there is a possible entropy contribution to some such thing, but those can be suppressed by suitable boundary conditions, and that is the explanation for saying that it is a solid subject to suitable boundary conditions. Okay, so here the boundary conditions have been chosen to select this particular phase. Okay. Okay, so this is the phase diagram this is in 3D. So in the Monte Carlo simulations, so this is the fluid phase and there is a solid phase, and at some pressure there is a jump in density. So it's a first order transition. When you change this fraction, which is the density, and this is the pressure, so you can say this is the independent parameter variable, and you get this. But at some density there is this, but if you keep density the same, the fluid state has a extension. So this is a super cool liquid and this is the superheated solid, or low density extension of the solid curve. So you can have the solid phase with the lower density, which is not really equilibrium, but it can be seen in Monte Carlo. Okay. And so then there are approximate analytical equations which describe these kinds of phases, something called Carnahan and Starling equation for hard spheres, and there is some similar equation for solid branch and coexistence, and there is a density jump. That is the points to recall. Okay. Yes, this is hard spheres. Okay, so now, what else can we do with hard spheres? So there is a back of the envelope calculation about the density entropy change at melting, which is very nice and instructive, and it's very hand waving. But it is quite amazing that this kind of hand waving calculation works so well. So I thought I will reproduce this argument here. So it says consider n molecules in a volume V. In a gas-like phase, the total phase space volume goes as V to the power n over n factorial. Now this is, you have seen it before, there are n particles, so each one of them has V to the power n, but factorial n takes care of the identity of particles. But if you are in a solid phase, each atom is localized in its own volume V by n, and the total phase space volume is V by n to the power n. And these look the same, except that factorial n is not equal to n to the power n. There is a correction factor e to the power minus n. So the change in entropy on melting is actually 1 in these units. Okay? It's the log of these divided by 1 by n, and it's of the order of kb. So you would say that change in entropy at melting will be 1 per atom for simple atomic solids. That is the prediction of this very rough argument. And this seems to be approximately satisfied for most simple solids. Simple solids are again solids which are in this class of atomic solids. Entropy measured in experiment has other contributions from increase in volume of melting and change in internal energy. So these we didn't, or these you can subtract. When you take the data, you realize that, oh, the actual change in entropy will also occur because there is a change. This is the change in volume. Sorry, at fixed volume, when you go from liquid to solid, there is this change. But if the volume changes, then there is an additional correction. So you can take those corrections into account and then calculate the change in entropy at due to melting, and that is 1 in these units. And here is, I just collected this data from internet. So melting entropy for some selected materials, aluminum, it is 1.45. It's pretty good. Given the very crude nature of the argument, the agreement is surprisingly good. Okay, of course, once in a while it is pretty bad, then you got to worry about these things. Okay, clearly it is not a universal number, but water is of course very strange material, so it has anomalies. Okay. So I guess that long justification given in the beginning was that it is good to study hard sphere melting transition in hard sphere model. So this is just a restatement of the definition. It says for hard spheres, all configurations of non-overlapping spheres are equally likely. Then the equation of state simplifies to P is equal to kT times f of rho, because the partition function is only a function of rho, density. There is no temperature. Then when you take free energy, it's kT times some function of rho. And when you take derivatives, pressure becomes kT times some function of rho. So it says the pressure will be proportional to temperature and some function of density, that we have to work out. So in this hard sphere model, there is no liquid gas transition, but there is a solid fluid transition as density is increased. In the solid phase, there is a periodic density pattern and there are sharp bragg spots. And in 3 dimensions, there is a density discontinuity as a function of pressure. And the exact equation in this hard sphere model is not yet known. Okay, this is another picture. This is 3D confocal microscopy picture of system of colloidal particles undergoing crystallization. Here the density is 0.4 of the close pack density, 600 seconds for 4500 seconds, so many seconds. You start with a very disordered state. The parameters are such that it's supposed to go to crystalline state. And with Monte Carlo, in time you get to the crystalline state. Okay, so these are hard spheres. Colloidal particles are the hard spheres. They are pretty good models of hard spheres. okay, because the spacing between them is much bigger than they are not in contact when they form a crystal. And so it is, the interactions between the colloidal particles can be negligible in this case, and they are pretty good approximation of the hard sphere system, okay. However, one can study other shapes because, once we are studying this phase transition into the solid, then it becomes important to know how important is the sphere. And so it turns out that you can study assemblies of other shapes, triangles, squares, hexagons, octahedra, cubes, long rods, rectangles. And the structure of the dense packed state depends on the shape. And so does the nature of the transition. The nature of the transition, whether it is first order or not, or whether all these things depend on the shape of the particles which you take to be hardcore particles. And so one can study, these kinds of stuff. We will discuss this in detail in future lectures. But it turns out that even these models are usually difficult. So not so much progress can be made other than Monte Carlo simulations. So we make even further simplification. We consider lattice models. Lattice models are where the centers of particles can only be put on a grid. And then they are, the size of the particles is bigger than the size of the grid. This is my grid, and the particle looks like this. And the next particle will be there. So, the centers of these squares are put on lattice points, but then they interact with each other, and so you can ask if these models behave in the same way as the corresponding continuum model. So it seems like there is not so much change in behavior if you go to the lattice model. However, lattice models are more convenient because instead of doing integrals over configuration space, I just count how many configurations are allowed, how many configurations are forbidden. So all the multidimensional integrals are somewhat more tractable if you study lattice models. And that is the reason for going to lattice models. Okay, so here, these are some very nice pictures I collected from this article by Barnes et al. And they take different shapes. And you can see what happens if you change the density of such hardcore particles as what happens to the typical configuration when you change the density of particles. These are all Monte Carlo simulations. This is low density, intermediate density, high density. These are squares, and these are rods. And as you increase the density, they look like that. And these are Z-shaped particles. These are called tetraminofluids or tetramers. And these are Z-shaped, these are L-shaped, and these are T-shaped molecules. And these pictures are sufficiently cute that one can try to understand the structure of the state irrespective of any other applications. But as I try to justify the interest from a physical point of view is that, okay, so this one we will come to later. I think one important point to realize in relating the hard sphere transition to the transition between real solids is that the hard spheres do not attract at all. So they don't form a bound state. However, if the real solid, of course, is a bound state of matter. So what you got to do is you got to add some attractive interaction to hard spheres to make it more realistic. Alternatively, you can just say, okay, I confine the system in a box, so I fix the density, the particles cannot fly off to infinity, then that is good enough. Then after that, I don't need the attractive interaction. I have fixed the density to be bigger than 0. So then I am doing okay, because the only thing the attractive interaction does is to give you, make the density non-zero. Once it is non-zero, then within that density, when the system goes from solid to liquid, there is a change in density. But there is not so much change in energy, binding energy per particle. And that energy change can be roughly ignored, or you can say that I can take the attractive interaction to be long-ranged, so that even when there is a change in density, the attractive part does not change. It's only the function of density. Okay, so that so there is a theory which says that if you take the interaction potential if Rij is less than sigma, this is the hardcore condition, and it's e to the power minus gamma Rij for Rij bigger than sigma. So this is gamma, and this is a gamma. So for any gamma, this is a attract minus V0. So there is some attractive part which is exponentially decreasing, but this gamma determines the range of the attractive part, and you let gamma tend to 0, then the attraction becomes very long range, and the limit of gamma goes to 0, the attractive energy between two particles gives a finite, goes to 0, but the total attractive energy of one particle in a sea of other particles goes to a finite constant. So that gives me the binding energy. And then for this model, the pressure as a function of temperature and density is equal to P hardcore, let's write free energy. Log Z, there is no beta. Okay, so this is the attractive correction which is proportional to rho square. This is like a mean field theory of some sort. So I can take the model, add a long range attractive interaction. It will not change anything in the limit of large size. It will just add a part which is proportional to density square. Then this system will show one transition which is the hardcore transition solid to liquid, and another transition liquid to gas which is like the transition van der Waals type transition. So you can get two transitions in this model with this provision. And the statement is that in discussing the solid to liquid transition, the attractive part of the interaction can be ignored or neglected. It is not so critical. Okay? All right. So now I want to come to the particular transition between long rods, which has been one of the shapes. So one of the shapes is that you have cylindrical rods which are very long, and the length of the cylinder is much bigger than the radius of the cylinder. This problem was studied by Onsager in 1949, and he did the calculation which I will do tomorrow in more detail. And so he showed that the second virial coefficient, he studied the long rod molecules and did the Mayer expansion for these and showed that the second virial coefficient can be calculated. Third virial coefficient is very tough to calculate. So he couldn't calculate the third virial coefficient in closed form. And so he said that, well, suppose you take the long size in anisotropy limit in which the length is much bigger than the width, but the some suitable way in which the length and width are related so that the second virial coefficient is constant. Then in the limit, let us say, I have a cylinder like this length is B, and this length is sigma, then B2 is equal to B squared sigma. This is the second virial coefficient is proportional to the square of this dimension and 1 power of sigma. And so you can take the limit in which B cubed sigma goes to 0, but B squared sigma remains finite. And then in this limit he showed that the third virial coefficient will go to 0 and the equation of state will become simple and exact. That's a sort of very singular limit, if sigma goes to 0, B goes to infinity, you get very long lines. And I think the argument is rather tricky and not fully appreciated generally. But the statement is correct. But he showed that this is actually discussed the fact that you can actually realize this transition, and it can actually be realized in tobacco mosaic virus particles in water. So what we wanted to do, we want to construct long rods in some moving freely in space. That's hard to do, but you can have rods suspended in water which can move around in water. So that is much easier than rods moving in vacuum. And he said that we can have long molecules which are rigid rod-like molecules which are suspended in water, and then you can change the density of these molecules and see what happens. I guess one can think of all kinds of molecules, but turns out that this tobacco mosaic virus has very long rod shape like, and all the virus particles have the same dimension, more or less. So they provide a much more easily realizable system than some chemical system I could have thought of to test these ideas. So he said that you take these tobacco mosaic virus particles and change the density of the suspension, and then you should see a phase transition. What's the phase transition? In the high density phase, you have these rods. They are in the solution which we are ignoring. So then at low density, there are just very few rods very far away from each other. Each one has a random orientation. Okay, so they move around without too much hindrance. It's like a non-ideal gas. But if you have high density phase, the opposite limit, where there is a maximum possible density and just a little bit below that. So you try to imagine needles in a box, and it is clear that they tend to become parallel. A typical configuration will have all rods nearly parallel. This argument is very intuitively obvious and clear. I mean, I don't have to write any equation to see this one. And so he said that it will make a transition to a state in which there is a breaking of orientational symmetry. All the directions are no longer equally likely, all the molecules lie in the same direction, And so he called them nematic liquids. And now, so nematic liquids are very special. They have the property that they are like liquids, but they are not isotropic liquids. The properties of the liquids, they are anisotropic liquids. But looked more closely, you break the translational symmetry of a liquid in some partially, but not fully. In a solid, that translational symmetry is broken in a big way. Here it is broken in a smaller way. So these are called mesophases, middle phases between solids and liquids. And there are many more examples of liquid crystals and liquid crystal phases now known. But this is a nice picture of a tobacco mosaic virus suspension. So one is so the liquid is below, and you shine light on it, look under polarizer. In the left hand side, there is no polarization. It is not a polarizing liquid, and so you don't see anything. In the right, there is the liquid polarizes the stuff in some way. So when you see under cross polarization, you see some structure. And this structure is at the centimeter scale, right? So these transitions are visible. Of course, nowadays you know that these transitions are visible. All your LCD watches or displays act on some general principle like that. And so these are visible examples of these phase transitions of long rod molecules. Okay, so lattice models of long rods. So one can also study lattice models of long rods instead of continuum models. I take, as we said, that we like to study lattice model. So the simplest model is like these long straight rods of length k. K can be any number you want, okay? And only hardcore interactions. And is there a phase transition as a function of density? That's the question we would like to ask. So in lattice models, the k equal to 2k is called the dimer model. And so you have a system in which you have these dimers which take two squares, and there are empty spaces. And you can ask that if you put these at random, what happens? So there is a proof by Heilmann and Lieb that there is no phase transition at k equal to 2. As soon as you put smallest density of holes, the system becomes disordered. It does not display any long range order. And we did some numerical simulations for 3 and 4. And in 3 and 4 also there is no phase transition. So one can ask what happens for larger D. And you know, there is a book by Dijon and Pro in 1995 where they discussed this model, and then they said that it is not quite certain that such a lattice model, even for large P, will lead to a transition. There P is our K. So even if you take large K, whether you get a phase transition in this lattice model. In the continuum model, the Onsager argument works, in principle works well, and there is a phase transition. The question is, does the phase transition survive in the lattice model? And this was not very clear at this point in 95. And the argument why it is not clear is also rather obvious. The point is this, that we are saying that there is a long rod, let us say k equal to 10 or whatever, then at high density they will become parallel. But suppose you look at the maximum close packed case where all the sites are occupied by rods, then at high density you can, full packing, at full packing you can construct a system like what is shown above, where you can take k by k rectangles and occupy them with either all horizontal or all vertical rods. And the number of configurations you can make like this, which are full packed, is 2 to the power n by k square, because n by k squared is the number of squares, big squares, and 2 for each such thing. So these many configurations are possible. But the fully packed state, which is orientationally ordered, are only 2, either all horizontal or all vertical. So they have no weight in the ensemble. Of course, the more general state is much more complicated. You can have complicated tilings. But the fully packed state is very unlikely. It doesn't have any weight. So it doesn't happen. So in this model, it is clear that at full packing, there is no long range order. At low density also, there is no long range order in orientations. So presumably there is no order at anything in between. That was the rough expectation, which is also borne out by these this rigorous stuff for dimers and numerical data for other stuff. In fact, if you look at that barn stuff which I showed you, here also there is no long range order. This is k equal to 4. So it is consistent with the general picture. Okay. However, so we did some Monte Carlo simulations of this system, and we've actually found that there are 2 phase transitions as a function of density. So initially, you have a configuration which is like this. This is sort of moderately dense but not very high density. It's 0.66 of maximum closed pack density. You have horizontal and vertical dimers, k-mers, but there is no long range order. Then you increase the density to 0.89 and almost everything becomes ordered. It's some, these Monte Carlo, so this thing can flip around and can go somewhere else, but roughly this configuration looks like that. But you go to even higher density, then you get, again, loss of order. Sorry?
You allow big jumps of position?
The algorithm for simulation is actually, I will discuss later. So that one actually does what we call track update. It updates a whole line at a time and not local moves. And we have checked that these configurations have equilibrated, in the sense that you can start with ordered state and you get to this one, or you start with a totally disordered state, you get to this one, or you start with a disordered state like this, but relax it, then it gets ordered in intermediate region. Okay. So here k equal to 7. So this one orders, but k equal to 6 does not order. So there is a minimum value of k at which you can see these kinds of phases.
6 has only one transition.
This has 2 transitions, one from the disordered state to this one. 6 has no transition.
No transition.
No transition at all. So here from disordered you go to ordered, from ordered at higher density you go to disordered again, which is somewhat surprising.
So do you have an image of how you go from the completely ordered state to the... What kind of moves do you have to make to go from B to C?
So we'll discuss in the next lecture. Okay. So similar things occur on triangular lattice. At high density, you get rods in 3 orders, but there is no long range order. But in intermediate densities, you again get nematic order in which all the rods are parallel. Okay. And so first transition, the first transition which is from disordered to here, this has been studied in Monte Carlo simulations by other people, and they seem to be in the Ising universality class. Because there are 2 ordered states, and if you take a random configuration, there will be an island of horizontally ordered state in a sea of vertically ordered states and vice versa. And so at large scale, they look like Ising model. And so this phase transition is, on these grounds, They are in the Ising universality class, which seems to check with the Monte Carlo. Monte Carlo evidence is consistent with the idea that the corresponding exponents are Ising exponents. The triangular lattice, you have 3 states. And so it belongs to the Q equal to 3 Potts model universality class. And the second transition is hard to study because the standard Monte Carlo dynamics involves all kinds of problems with jamming. So that is the issue there, which Professor Lubensky has also sort of asked. How can you be sure that this is what's happening? Okay, because most of the algorithms people use to study these transitions have a problem with jamming. So once you reach a configuration, there is no way to go to it except erase the whole thing and restart all over again or some such thing. And then one doesn't know if you have equilibrated or if you do the simulation again, you will get similar results and so on. Okay, so we had to devise a different algorithm which takes care of these jamming problems. This algorithm doesn't work. I will discuss it in detail next time, but this doesn't work at full jamming, but at least at 0.95 density it works quite okay. You go to even further density, then even this algorithm doesn't work so well. But 0.95 is beyond the transition point. So near the transition point it works quite well, and we can be quite sure that the simulations are well behaved. So we will call these 3 phases: isotropic, nematic, and high density disordered phase. And we'll try to understand what happens there. Okay? And I think this we will discuss next time. And so I want to stop here and let you ask some questions about the stuff we did so far. So to summarize, firstly I said that, what is a phase transition? It is a phase is an answer to a yes-no question. And so phase transition is where the yes changes to no when you change a parameter. So then we said that there are these phases, solid, liquid, gas phase, and can we understand them? We said the good model for understanding them is something like a Lennard-Jones interacting set of molecules. Then we said that if you want to understand the solid-liquid transition, then one can ignore the attractive part and only deal with hardcore part. And that provides a moderately good description of the melting transition. Sort of heuristic evidence was that a very sloppy argument about the entropy of melting seems to match with the actual observed data to good accuracy. Okay, so then we discussed the hard rods. And so this is the model of hard rods. Oh, I think we will go even here somewhat later. The Onsager argument and variations of the Onsager argument we like to do in some detail later. This is the experimental verification of this isotropic to nematic transition in real systems. This is the model, and this is the argument that at high density you will not get long range order. And this is the Monte Carlo data that there are actually 3 phases. One is the low density phase, the low density disordered phase, the intermediate density nematic phase, and the high density disordered phase. Okay, so we will stop there.
You said that if we change the shape of the molecules, that is from hard rod, sphere or rectangular shape, the order of the phase transition will change.
Yeah.
So let's say
change. It doesn't have to change always, but it could change with change of shape.
Okay, so if we have a let's say if we have a spherical molecule, and if we continuously change the shape of the molecules to sphere to rods, so what happens?
Okay. Yeah, so I guess this has not been studied in great detail, but if you take ellipsoids, which are change of shape of the sphere, then I guess for small changes, nothing happens. But if you make a large change, then it will change to a different behavior. So at large enough aspect ratio, it will look like long rods. At small enough aspect ratio, it will look like sphere. But in between, will it jump from this behavior to that behavior in one step, or will it show other intermediate phases? That I cannot say just now. It has not been well studied. People can do actual experiments with things like candy. You know, there are these candies which are kind of ellipsoidal molecules. You can fill them in boxes and you can try to see what is the phases you get. Okay? And the simplest thing one realizes, which is interesting also, is that the maximum closing packing fraction you can get with ellipsoids is higher than with spheres.
I have
So obvious.
I have another question. That why we are not getting any phase transition for k is equal to 6? That point I don't get.
Okay, so I don't know. We don't know the full answer. That is the kind of stuff we want to understand. So I was trying to pose the problems, set the general scenario. Then we'll try to address some of these questions in some detail to get a theoretical understanding of these issues if possible. Some answers we will not be able to give. So in particular, why does it happen that dimers don't show a phase transition? Forget k equal to 3, k equal to 2. And now I said there is a proof due to Heilmann and Lieb which shows this. And now what is the proof? The proof kind of says that if you take this partition function, then the zeros all lie on the real axis, and so there is no phase transition. But that is sort of a mystery. Why do all the zeros lie on the real axis? Who told them lie on the real axis? No, something like this. So sometimes even the rigorous proof does not provide a real understanding. What I call real understanding, some intuitive feeling for why it happens or some such thing. It may not be there even though you have proved the result rigorously. So my argument just now will be, I don't know what happens at k equal to 2, but 3 is the same as 2. It behaves in the same way. But 7 is, so there is in the space of k, there is a low k behavior and there is a high k behavior. And right now we can only jump in discrete steps from 6 to 7. 6 is low k, 7 is high k. Yes, sir. Can you use the mic, please?
How do you calculate pressure for hardcore assemblies?
Okay, so that is an easy question. The question is, how do you calculate pressure for a hardcore system of particles? I'll give a formal answer and then I'll try to give a better answer. The formal answer is this. You take a box of size V and there is a grand partition function which is, Z is called activity, and you take rods omega n is the number of ways of placing rods which are small n non-overlapping rods in this lattice, and omega z is the, attach a weight z to the power n, sum over all n, that gives you omega z, and log omega z kt is defined to be the pressure. This is a general formula, Landau potential. So you calculate the partition function in the grand canonical ensemble, and then the Landau potential gives you the pressure. That is the definition. Now, I understand the question is not dealing with this. The question asks, if you have hardcore particles, then where is the pressure coming from? So what we do in this problem is we ignore the potential, the kinetic energy of particles. These are chargeless, there is no charge. Okay, so you have hardcore particles, but they have no kinetic energy. The kinetic energy integrals have been done away, and we are only discussing the configurational integral which depends on density. So they have no kinetic energy, so where is the pressure coming from? So the answer is there is an entropy which is a function of density, and the derivative of entropy with volume will be called pressure. This pressure is proportional to temperature in the sense that, that takes into account the, so why is the derivative of entropy with volume the pressure? That sort of, I think you know this answer, so then I will not explain this point. Yes, sir. Yes, yes. Of course, you can study the sublimation process also. In these models, you cannot study them because, as we said, so in these models, there is only one phase transition from solid to liquid. And so the liquid phase or fluid phase is the same, its gas and liquid are the same. But if I study the model with this extra coupling, then I think it is perhaps one will be able to get the distinction between liquid and gas, and you will get transition either to the low density disordered phase or the high density disordered phase. And that will be the difference between sublimation and melting. Yes, sir. Very good. So the point is that in the hardcore models, the energy is either zero or infinite. So there is no notion of energy. And so there are only configurations, and some are allowed, some are disallowed. There is a notion of entropy, which is a function of density. But if you want to convert the entropy into free energy, you have to multiply by kT. The energy is always zero, but F equal to minus kT times S, minus Ts, okay. So entropy has to be multiplied by temperature to give free energy. So temperature is just a conversion of the entropy to energy scale.
This scale, is it the dynamical rules? Are you evolving the system?
Actually, in these models, there is no, I can discuss all this stuff without using the word temperature once, and it doesn't come into picture. The pressure will be called reduced pressure. P by kT is a reduced pressure, it's only a function of density. So I will determine P by kT as P tilde, and that doesn't use the word temperature anywhere.
Which is changing in your system.
Yeah, it's the density which is changing, and the pressure is a function of density.
So Deepak, I had one question. So you said like for the Onsaker found the second virial coefficient, and then he could somehow see that there's going to be a transition. Right? Yeah. So for hard spheres, I think people have calculated many orders of with the coefficient. From there, is there also an indication that there's like can one see similarly say anything about the transition from the?
Unfortunately, no. So what happens is that actually some 12 virial coefficients are known, but you need to know the asymptotic behavior of these virial coefficients. But they don't determine the first order transition which occurs. So the asymptotic coefficients determine the radius of convergence of the virial expansion. So the actual transition preempts the possible transition which would have occurred due to these virial coefficients. So the first order transition preempts the critical transition if there is one. Okay, so it's a more subtle stuff.
So if there are no other questions, we break for coffee and meet at 11:30.
Okay.